Okay, sorry about the delay. So I've got it working finally. Actually needed to work, otherwise I can't record it. So, okay, so firstly, there is announcement of the quiz. Quiz will be next lecture. Right, okay, so you're aware of that, which is good. So it will cover everything up to end of chapter 19. Sorry, this is the wrong slide. Let me fix that. Yeah, so we've just started Kinetic Theory of Gases, and so we will try and get to the end of this chapter today. Not going well. Okay, there we go. Right, yeah. End of Kinetic Theory of Gases. And so we'll have the quiz next lecture. It'll be a 45-minute quiz. It'll be much like last time. For those of you here in Shanghai, obviously people in this room, I'm talking to also people in the video. So you will need to do it under exam conditions, and then I will email the quiz questions for those of you who are remote. So this will be good practice for the final. The kind of questions that you might get in the final will be rather like in the quiz that you'll get on Tuesday. There'll be one final lecture Thursday. That will be the last lecture, and that's also when the final reports for the assignment are due. So please hand them in then. Just by email is fine. You don't necessarily have to print them out, but you can also give me a physical copy if you like. And and then in that lecture we might just start the last chapter, which is chapter 20. I doubt we'll get through it all. Alternatively, if you want to do particular revision questions, and we can also do that as well. So you can come prepared with your questions for that last lecture. Okay, so any questions about the quiz? Okay, if not, then let's get on with chapter 19. So just to recap, we were talking about, so this chapter is about, a microscopic theory of gases. So this is why things like Avogadro's number and things like that come into it, number of moles. And you might have, of course, seen this in other subjects, but one thing that we will be using is the ideal gas law, so PV equals nRT, or the microscopic version is PV equals nKT, where the N is the number of atoms this time. And from that relation, we could work out things like the work just by directly integrating that relation. So work is integral of P with V. So if you put in the ideal gas relation, then for constant temperature, you can integrate it. And then you can get a relation like this. But keep in mind that only works for constant temperature. For any other process, it does not necessarily follow this formula. We can do that because, the temperature comes outside the integral, and then you just integrate the volume. So constant temperature relations or transitions look like this. Basically 1 over V on the PV diagram. For constant volume processes, we already saw that work is 0. For constant pressure, it's just P times the change in the volume. We spent some time doing this kind of derivation. So this was an attempt to kind of derive PV equals nRT just from a microscopic point of view. And you can get a lot of the way there, so you can get a relation. If you put this V on this side, then you get something that looks like PV equals N something something. And then so if you relate that to something to RT, then what it basically tells you is that the velocity of the atoms, actually the root mean square velocity, is equal to something given by the right-hand side here. So what's interesting about this relation is that it's only dependent on the temperature in terms of our state variables. So there's no pressure, there's no velocity, nothing like that. It's only dependent on temperature. And if you actually recast that into an energy formulation, so we've got an equation for velocity here. So if we put that into half mv squared for the kinetic energy, then in fact we even get some further simplification, which is that the kinetic energy is only dependent upon the temperature. So very interestingly, the kinetic energy is really very intimately connected with the temperature, right? Kinetic energy of the gases. So that's like quite a key concept in all this, and so this is where we got up to. So where we'll start off is talking about the mean-free path. So this is what this is obviously if you've got a bunch of atoms in a container like this, then the atoms are going to actually bump into each other, right, eventually, because there's a lot of them, and if they're moving around randomly, then they won't just bounce off the walls, they will also bump into each other. And so this is an expression, or this formula here down the bottom is talking about what is the distance before an atom will bump into another atom. So as you can see from here, here's an atom, it might be injected here, it might bounce off this atom until it hits this one here, and then it'll go this way, and has this sort of random movement throughout this space. Obviously, occasionally it will also bounce off the walls as well. So how can we work out, this mean-free path? What is the distance that an atom will travel before it bumps into something? So the way that you can work this out is to think of it like this. So obviously the atoms have some kind of radius or diameter in this case. So if we got a bunch of identical atoms with the same diameter and they have some mass m, right? Then first let's think of the situation where all these atoms are like not moving in this space. So say you got all these other atoms here kind of frozen in space, just as a simplification, and then we're going to shoot an atom in, and then we're going to figure out how, what is the average length that it would be moving before it bumps into another atom. So it'd be sort of, in this case, the diagram would be like an average of all these lines here. So the way that we can work that out is like this. So if you've got like two atoms like this, then the distance between the atoms are like this d. Or if another way to think about it is that if we think of this thing that we're injecting here as just like a point, and all these other atoms as just fixed balls, then an atom will collide into another atom if it's within a distance d of the center of another atom. So in this case here we've got this is, say, the fixed one, and this is the mobile one. Then if this is like d this way, then it will collide with the atom, right? Or it could be d on the other way, so it could be d distance this way, or of course it could be d above or d below, or in fact, any circle that's got a radius of d. Okay, so the kind of region of collision for this fixed atom is going to be like this. So it's like a radius of d surrounding this fixed atom, and this other one we can just forget about the diameter. So in this way, we can just think of the diameter of the fixed atoms, and we don't really have to think of the diameter of the thing that's moving. So this is kind of like the region of collision, right? Okay, and then what we can do to work out the mean-free path is to say, all right, well, let's figure out. Let's suppose that this thing is coming in at a velocity v. Okay, and then the distance that it would move in some time interval would be the velocity times the time. And then what we can do is to say, all right, well, so when this atom is moving here, oh, actually, sorry, I think I got it the wrong way around. So, sorry, this one we can think of as the mobile one, and this dot as the fixed ones. Okay, so basically, yeah. All right. So we're starting off with something like this. So these are the fixed atoms. They're all got diameter d, and then this is the one that we're going to shoot in from the side, right? Okay, and this one is going to come in like this, and we're going to figure out, which atoms it might hit. And so basically, what we're going to say is that this is basically equivalent to saying we have the fixed atoms as dots. Okay, so sorry, I think I got it the wrong way around before. And then instead of having this one as diameter d, we're now going to have the mobile one have a kind of a region of influence of 2d. Sorry, this is the diameter. So I've drawn it wrong again. Okay, here diameters, and this is diameter, right? Okay. And so this ball of diameter 2d is going to come in, and we're going to figure out which atoms it's going to hit. And so obviously, so say it's coming in like this. So basically the idea is that we just have to count the number of points that are inside this cylinder, right? Because basically any point that lies inside the cylinder will be a collision, right? So if we have to, so basically the idea here is that the mean-free path is going to be the length of the path during the time t divided by the number of collisions in time t. So, because this time t that we just picked is kind of arbitrary, right? So, say we just chose 1 second or something, and then say what we find is that it collides like 7 times, right? And then in that case, we can say that the frequency of the collision would be 1 second divided by 7, or in this case, what we want to work out is the mean-free path. So then we would just say, okay, if it travels a distance of, say, 1 centimeter in that time interval, and it hits something 7 times in that time interval, then it would be, for example, 1 centimeter divided by 7. Right? So that would be the mean-free path in that case. So what we're working out here is like the distance divided by the number of collisions. And so now all we have to do is just count the number of dots that are going to be inside this cylinder. And if we know the density of these atoms, so that's the number per unit volume, multiplied by the volume of the cylinder that this is sweeping out, then what we'll get is this expression, and then the v's cancel, the delta t's cancel, and so we get something like this. So 1 over pi d squared, and then n over v. So that would be the mean free path. Now, remember we made an assumption that the atoms that were here were kind of fixed, right? These blue ones here, we said they were fixed, whereas this red one here on the board is actually mobile, right? So we made that kind of assumption, which obviously it's sort of a simplifying assumption, and I won't go into the details, but if you take into account the actual movement of the background atoms, so if you now make all these background atoms move, then you get a slightly different estimate for the velocity, because now there's like a relative velocity between the atoms. So it's not just the velocity of the thing that's moving, but it's the velocity of everything. So if you take that into account, there's an extra sort of numerical factor that you need to include, and so the final formula looks like this. It's basically the same, except there's a root 2 here. Okay. So just as some example numbers, for example, if you take the atmosphere, like air, and if you look at the mean free path at certain altitudes, obviously the density of the air gets less as you go higher and higher. So, for example, at sea level, so roughly where we are, the atoms are bumping into each other at a distance scale of like 0.1 microns. So that's, it's very, very small. You can't even see it with your naked eye. So all the atoms in this room are bumping into each other like really constantly, right? But actually already at, 100 kilometers up is already quite high. That's already at the level of some, maybe some satellites are more like 200 or 300 kilometers. But so once you're at that kind of orbital kind of heights, the mean free path is much, much bigger. In fact, so 100 kilometers is 16 centimeters, so that's a lot bigger than 0.1 microns, but just at 300, it's already 20 kilometers, so the density of the air is very, very low, obviously, there. Okay, this formula will be in the formula sheet for the exam, so you do not have to remember this one. But you should, certainly know what it means and stuff. Okay, so let's look at this question. So 1 mole of gas A with molecular diameter 2d and average molecular speed V0 is placed inside a certain container. Another mole of gas B with molecular diameter d0, so half the diameter of the other one, but twice the speed, so 2v0, so the molecules of B are smaller but faster. It's placed in an identical container. Which gas has the greater average collision rate within its container? And maybe I'll write the formula for the mean free path. All right. Yeah. Okay, so that's the formula for mean free path. So how about we start by figuring out, so which one has the larger mean free path? Right, yes, B, yes. And so, so you said that because the diameter is smaller? Yeah. So, yeah, so the interesting thing that this question brings up is that, so you would intuitively think it's dependent upon the velocity, right? So you think, yeah, okay, so it's moving faster, so it should have a larger, or it should hit other atoms more often, right? But actually, it's not dependent on the velocity at all. It's only dependent upon the diameter of the atoms and the density. This n over v, that's the density of the atoms, and then this is the diameter. So it's really only dependent upon the diameter. The velocity actually kind of cancels out at this point, so you don't even have to think about the velocity. Right. So basically, the answer is B, because for the Meanfree path, that is. So the smaller the diameter, the less likely it's going to hit something, and hence the Meanfree path is larger. But now to answer the question, so which has an average, greater average collision rate. So collision rate means like it bumps into stuff more, right? So higher collision rate means it bumps into stuff more. So we're looking for the one with the smaller Meanfree path. So to answer the actual question, I think it would be A, right? So I mean, so it's easier to just do it in two steps. Think of the Meanfree path first, and then convert that to collision rate. So the one with the longer Meanfree path is B, but then higher collision rate is actually A. But yeah, the interesting point is it doesn't depend on the velocity. Okay. So a couple of slides ago we did we worked out this relation where this is the velocity of the atoms moving in a particular container. And then we could work out that actually it's only the velocity itself is related to the the temperature and also the molar mass. So this sounds like this formula sounds a bit like, okay, all the atoms are moving at this velocity. Obviously, it's not true. It's, the motion of the atoms in a gas is extremely random. Some will be moving faster, some will be moving slower than this. So in fact, there's a whole distribution of different velocities it's actually moving at. This is just, some kind of average, as I'll explain what that really means in a minute. So if you look at the actual speeds of an atom, there will be a whole range, as I said, and this Maxwell's speed distribution law gives a formula for that distribution. Again, we won't really derive it, but it's basically derived in a statistical way. So this is the probability that an atom in a gas will be moving at a particular velocity. So, for a particular velocity, put in this formula, and within this formula it's got a bunch of constants related to temperature, the molar mass of the atoms, and that's it actually, and gas constant. And this will basically tell you the probability that it will be moving for that particular velocity. And the graph of this looks something like this. At zero velocity, that means the atom is completely not moving. The probability of that happening is basically zero. So at any non-zero temperature, you will always have the atoms will always be moving with some velocity. It's basically impossible that they're completely stationary. and then it reaches some peak, and it goes down again. So here it's saying that some of the atoms are moving quite fast, but it gets less and less likely. In fact, as you go to higher temperatures, this drops off sort of exponentially. Well, it's actually e to the minus v squared even, so it drops off even faster than exponentially. And there's sort of a most likely kind of velocity. And so what you can do, this is actually a probability density, just in case. So have you guys done probability densities? Okay, well, at least some of you have. So basically, probability density means that the probability variable, in this case v, is kind of continuous. Okay, so because it's continuous, I did say that this is the probability, but strictly speaking, it's actually the probability within. So the actual probability will be that formula there within a particular range. So v, I don't know, v min to v max. So basically, if you want to work out what is the probability within a certain range, what you do is you integrate that probability within the limits. So say you wanted to work out, okay, so because it's basically impossible to, because this is a continuous thing, if you say, okay, what's the probability of the atom moving at, exactly 300 meters per second? Well, exactly 300 is basically impossible because, if you measure it, it'll be like 300.01, or, won't be exactly 300. So usually what you have to do is to pick a certain range. So you say, okay, what's the probability it's going to be between, say, 300 and 400? Okay, and then this can give you the probability, because then what you do is integrate. So strictly speaking, it's actually the probability for a particular velocity range, right? Okay, so anyway, so it's basically peaked at some point, it goes down, and it starts at 0. And for lower temperatures, this peak tends to move to the left, okay? And so for higher temperatures, it moves to the right. Makes sense, because the hotter the gas is, the faster in general it should be moving. Although, there will be a spread, but in general, it'll be moving, all the atoms will be moving faster. So what we can do is calculate things like the average velocity. And in order to calculate the average of a probability density, the kind of thing that you do is, so this, in terms of the average velocity, let's get the notation right, the average, right? So you do something a lot like, so when you take an average of a quantity, what you do is you multiply the probability of that occurring times by the value, right? So if I'm taking the average height of everybody in this room, then I would multiply the height by the number of people within, for a particular height, right? And then, so here's basically like the number of people, the number of statistics that I have, and then this is the value, right? And if you calculate that, then it gives some relation like this, 8 RT over pi m. Now the thing that we actually calculated before also appears here. In fact, this is maybe the more relevant quantity often. So in this case, root mean square. So it's actually calculating the average of the velocity squared, and then you take the square root of that whole thing. This is actually usually the more relevant quantity because the velocity squared is related to the kinetic energy, right? Because it's half mv squared. So that's why actually taking the average of this is more related to like the kinetic energy and the energy of the thing. So that's why people are interested in this. But you can see that it basically has the same form, right? So, okay, this is square root of some numbers but basically the variables here are like RT over M. Over here it's also RT over M, so, 8 over pi is something a little bit, I suppose 2 point something, right? Under the square root. And then here it's 3, right? And this one is like the location of the peak here. So if you, took the derivative and then found where it's equal to 0, so basically solve this equation, dp equals 0, then that would be equal to this one. Yeah?
RMS just means for one molecule.
No, it's just like this thing is giving like statistics of kind of all the atoms, right? So if you view it as a statistical thing, like you take, well, yes, one atom, yes, but you say you pick one atom and then measure its velocity. Now, it will be anywhere kind of in this range, randomly, and then this will be like the probability of that. So if you pick 10 atoms, then what you're probably going to find is most of them are around about, in this case, say 400 meters per second, right? But maybe like you just pick a strange atom which is moving like, very fast or maybe very slow. So once in a while you might get a very fast or very slow one, but most of the atoms will be moving within this range. Right? And then this average is just saying, okay, so say I pick 10 atoms like that. What's the average speed of that? RMS is saying, okay, I'm going to square the velocity, average that, and then take the square root. Okay, sounds a little bit strange, but it's kind of more related to the energy of the thing. So that's why, because half of mv squared. So it's sort of like taking the energy average and then square root. So, and then this one is just the peak, the most probable speed. So this is the most likely one that you will always get.
Why do we need to square root of v and check the square root?
Well, basically because we don't need to do anything, I suppose, but it's just sometimes some quantities are used in different ways. We take the square root here because, firstly, otherwise the dimensions won't even be a speed, right? So if you square everything underneath the square root here, the dimensions of this thing will actually be meter squared over second squared, right? So it's definitely not a velocity, right? But then if you take the square root, then we're back at meters per second squared. So it's definitely different to this one. So it's not an average velocity. So it's slightly different. But roughly speaking, they're all the same. So I mean, you can see that the formulas are okay. They're different, but roughly they're all the same. So they're only different by maybe a factor of two, not even two difference, right? So under the square root, 8 over pi, as I said, is I think 2 point something, and then this is 3 and this is 2, right? So numerically they're all very similar, and you can see that also in this graph. So VRMS is maybe the slightly bigger one. V peak, that's the peak of this graph, is there. It's the lowest one. V average is somewhere in the middle. Okay, so just to give you a few sort of more physical examples of the relevance of this, right? So, for example, if you look at evaporation, if you got a bunch of atoms, things like a liquid does not need to be boiling for some of the atoms to turn into basically a gas. Actually, if you just leave a cup of water on the table for half a year or something, it'll probably be gone by the end of that duration, because basically things dry up, right? So that means that basically the faster atoms will actually just sort of fly out of the container, right? And this is basically because this thing has a tail like this. It goes, and so some of the atoms will be moving actually pretty fast. And if that atom just so happens to be near the surface, it will just fly out of the container. Right? And that's basically what evaporation is. Another example is nuclear fusion. So actually, you think that, okay, so the sun is at, I forget the temperature of the sun. Anybody? 6,000 Kelvin? Can't remember. Anyway, it's quite hot. You think that that's hot enough for fusion to happen. Actually, not exactly. That's just hot enough so that sometimes some of the atoms have enough energy for fusion to occur. And, basically it needs to be often enough so that it's self-sustaining, right, fusion. And this is kind of, so basically these high energy atoms can fuse and perform this fusion nuclear reaction, but in general, bulk of the atoms are not actually hot enough to do so. Okay, and so this is just a kind of an application of the thing we were talking about a couple of slides ago. So we said that before that the kinetic energy of an atom is 3/2 kT, right? So the internal energy, which we kind of hypothesized, when we were talking about the first law, we were saying sort of something like, okay, first law says that delta E is equal to Q minus W, and we were saying that this was a kind of conservation of energy relation, right? So there's only sort of two ways that the energy of a gas can change. It could either lose or gain it by heat, or the gas might do work and it might lose or gain energy that way. Now, we just sort of proposed this quantity of delta E, but actually now we're in a position to really write down a formula for what actually delta E was. We never really said kind of, what it really is. We just sort of said it has some energy and it's related this way, but the way that we can write down the internal energy is to is to basically simply multiply the number of atoms by the kinetic energy, right? Kind of makes sense because we've got a bunch of atoms, and this 3/2 kT, we were saying that's the energy of a single atom. Okay, well, the total energy of the whole system is obviously the n times that, right? So 3/2 kT times n, and we can so 3/2 n kT, and then we can just rewrite this in terms of the number of moles. So number of mole, n is number of moles times Avogadro's number, and then K was defined to be R over NA, So these NA's cancel. So 3 over 2 nRT. So we can actually write down an actual formula for the internal energy. And we can make the same points that we did before, that the internal energy of a gas is only dependent upon the temperature, actually. What we said there before was that the kinetic energy of gas is only related to temperature, but now we can basically make the same point about internal energy. So the internal energy is a function of temperature only. So actually this is quite sort of useful in terms of the PV diagram here. So previously we just drew, for example, constant temperature processes like this. And the PV diagram, we could, work out things like the work. We say, okay, we integrate under a particular process, and then we get the work, for example, on the 2, you integrate this area, and that's the work. But actually, this now gives us a very powerful relation in terms of determining the internal energy, right? So we just by looking at the PV diagram, we couldn't really work out what the heat was. But now, actually, using this relation, we can actually figure out that the internal energy along an isothermal process like this is actually all the same, right? So any point like along this isotherm, the delta E will be 0. So if this is, so any process, for example, if you say start here at some temperature, goes to a different temperature, T plus delta T, and suppose, it could go straight up, straight across, or some other place like this. Now, previously, we couldn't really say anything about what delta, what is the change in internal energy. Because, well, we could work out what the work is, but we didn't know what the heat was, and so it was sort of inconclusive there. But now we can. In terms of the internal energy, all these processes will be the same, because it's going from one temperature to another temperature, and then all these final points have the same temperature. So it's actually quite an important conclusion here, that basically along any isotherm, the internal energy will always be the same. Okay, so internal energy of an ideal gas is a function of temperature only. Okay, change in the internal energy of a confined ideal gas depends only on the change in temperature, not on what type of process produces change. Okay, it's kind of similar point. Okay, right. Okay, so yeah.
Can you? I'm confused about the relationship between the 3 ends. Like, what do they mean?
Okay, so N is a number of moles. Number of moles, right? N is the, okay, I'll write it out. This is the number of molecules. So, and Na is Avogadro's number. Avogadro. So 6 times 10 to the 23. So number of moles is just like, it's just different units basically. So this is just N divided by Na. So instead of saying, I've got a jar of some gas, I have, 70 times 10 to the 23 atoms here, which is like such a big number, right? It's just much easier to say, I've got, 10 moles of the things. yes, so there's that, but the main important point here, and I hope everybody gets it, is that along an isotherm the internal energy is all the same. Okay, so just please remember that point. All right, and so now we can start to make some connections between the three quantities that appear in the first law. So we've got, delta E, we've got, E, Q, and W, right? And for all different types of processes, so we're going to look at things like constant volume processes, constant pressure processes, adiabatic processes, and so forth. And what we can do is to actually start getting explicit expressions for the heat, the work, internal energy change for all those different processes. Okay. All right. So we're going to go through different expressions, and maybe what we can do is start sort of filling in a table here as we get all these results. Okay, so first let's do constant volume. Okay. So we did a while ago that heat is, we can write a relationship for the heat basically in terms of this heat capacity. And the heat capacity was like the conversion, if you like, between the temperature change and an actual energy, right? So if something goes up by 1 degree, how many joules of energy do you need to put into that in order to make that change, right? So the heat, we can write a formula like this down. Okay, so this is N CV and then times delta T. Now for a constant volume process, we know that the work is 0. Okay? And because delta E is Q minus W, so obviously this means that this one is also NCV times delta T. Okay? But so far it's more or less just definitions. This one was 0 because, P to V, right? But actually we just worked out this formula for the internal energy up here, right? So in fact we also know that this is 3/2 N RT. So actually, So actually, we can get an actual expression for what this CV is, right? So because we've got N delta T. Sorry, I should say we're doing change in energy, and only the temperature is changing here. So we've got delta T here. So we've got N delta T, N delta T. So CV must be equal to 3/2 R. So that's quite a neat prediction that we can actually make, just following from the fact that, using this relation that originally we said that the kinetic energy is 3/2 kT, and that came from working out a relationship, from the microscopic theory we could work out what the velocity of the atoms are, and then we can kind of deduce what the kinetic energy was, and then from that we can actually work out what the heat capacity is, right? So we could actually make a quantitative prediction for the heat capacity, and this is something certainly you could measure, right? Because you can get some gas, you can heat it up, and then you can work out how much energy it took to heat up the gas by a certain number of degrees. Okay, so actually this 3/2R, it certainly works for some gases, but then what you find for some other gases, it doesn't quite work. So sometimes you get something that's a bit more like 5/2R, sometimes you get like 3R, and I think we'll come back to this point, but this has basically got to do with the fact that when we did our derivation of this 3/2 kT, we didn't really take into account of the fact that these could be molecules that could be rotating or anything like that. We just thought of them as balls. We never thought of them as molecules or anything more complex than that. So if you take that into account, then basically you can argue that there are so this kinetic energy should be modified in the case of diatomic, meaning like atoms, molecules with two atoms in them, or polyatomic molecules. We'll come back to that point. Okay, so this one's frozen. Okay, so now let's look at another process, which is constant pressure. So for constant pressure, what we can do is just define this one. So in this case, well, this is more or less just definition. So if you have a heat capacity of something, in this case, this Cp means the constant pressure, right? Heat capacity. The work in this case will be, so remember work is P to V, but because it's constant pressure, it's actually, this can come outside the integral, and it's going to be just P times delta V. And if you use PV equals nRT, then this is going to be nRT times the change in temperature. So actually we can work out that the work is nRT, nR delta T. And now if we use the fact that if we just combine these two relations, then this change in internal energy should be right. So pressure right, yeah. So the change in internal energy should be basically just the difference between these two. So C E T minus T. This thing should again just be equal to 3/2 nR delta T. So if we just rearrange this equation, then we can figure out that Cp delta T, and then just put this on this side. So, well, yeah, well, Okay, so usually the way that people write this is, because this is CV 3 over 2 nRT is CV nRT. So usually the way people write this is it's like this. And so N times CV plus R. So basically the relation that you can see here is that basically the heat capacity for constant pressure should be different by the heat capacity for the constant volume by a factor of R. Well, it's not a factor, sorry, addition of R. So, just to recap, so this is just the definition, right? This is delta E Q minus W. And then this one, basically we just used this relation here for the internal energy, which should always be true no matter what the relationship is. The internal energy is only dependent upon the temperature, not the process, right? So we're doing a constant pressure process, but it doesn't matter. The internal energy change should always be equal to that thing. Just for the purpose of what we're doing here, we just wrote it as NCV instead of 3 over 2 nRT, but it's basically the same. And so we can deduce that actually heat capacity for constant pressure is CV plus R. Okay, and sorry, this one is frozen now, so we're just going to go over here. So you can see over here that so this is for a monatomic gas, right? So the constant volume heat capacity here is 3 over 2 nR delta T, but then the constant pressure is different by a factor, by another factor of R. For diatomic, it's the same. Constant volume is actually, I think, 5 over 2, and then 5 over 2 R, and then this one will be 7 over 2, so it's always different by a factor of R. Okay, so let's try this question. So the figure here shows 5 paths traversed by a gas on a PV diagram. Rank the paths according to the change in the internal energy of the gas, greatest first. Try and fix this in the meantime. So, well, firstly, what do you notice about these 4 paths here? 1, 2, 3, 4. Yep. Right. Okay. So you've jumped to the answer already. So yes, B is correct because 5 is the only one that goes between this isotherm, so this is all one temperature, this is another temperature. So it goes from T1 to T3, and the way that these isotherms work, the further sort of up they are, the higher the temperature, okay? Because of PV equals nRT, right? So this one is going from T1 to T3, and T3 is got the highest temperature, whereas all these other ones are going from T1 to T2. So in fact, what it will be in terms of the internal energy, because the internal energy is only related to temperature. So this one will have the greatest change in internal energy. And then 1, 2, 3, 4 will have all the same change in internal energy. It's purely temperature dependent process. Okay, and yes, so this is the point about the heat capacity being different for monatomic, diatomic, polyatomic molecules. And basically the point is that when we calculated this, well, when we remember this came initially from an estimate of the velocity of the atoms, and then we turned that into kinetic energy, and now we turn it into internal energy, right? And so this three originally came from some argument where I said something like, okay, well, we have some box, and then these atoms, let's say initially the atom is just bouncing left and right, and then what we were trying to calculate is the pressure on the box. And then what we did was to say something like, well, actually the velocity is not just moving in this x direction, but it's moving in the y and z direction. And there's live in three-dimensional space, so there's 3 different directions it could be going. And so these other ones, like vy, vz, they should all be the same, and hence the x squared should be actually a third of the actual velocity of the thing. So it was related to this dimensionality here, right? But we never really considered the fact that the atoms could actually are not just balls. They could, if they're diatomic, they could be spinning, and so this is a completely phenomenological type of relation. But what people noticed is that, okay, well, for monoatomic, it seems to this heat capacity of 3/2 R works pretty well. But for diatomic, it actually looks more like 5/2 R. And for polyatomic, it looks more like 3R, which is like 6/2, right? So people said, well, maybe it's got to do like the number of degrees of freedom, right? So here, this 3 came about because, okay, there's 3 ways that this atom could be moving, but we didn't count any spinning. So let's count the number of ways that like a diatomic atom could spin and have a decent amount of kinetic energy. And so a diatomic could spin like along this axis or maybe this axis, right? But if it spins like this way, like this twirling kind of thing, it wouldn't have much energy. So this gives like another 2 degrees of freedom. And then for a polyatomic thing, which has got something like this, then any degree of rotation would also contribute. And so if you take all that into account, then you should have a heat capacity at constant volume that looks like this. So, F/2, where F is the number of degrees of freedom that the atom could potentially move in. So that's not just translational movement, so 3 dimensions, so that's at least 3. But then if there's like rotation, then that would add either 2 or 3 more degrees of freedom. This is a very rough formula. It's not really like a rigorous derivation. It's just like you look at the data and you go, yeah, it looks like this. Yeah. Okay. Let me skip this, but basically, I just say that it's, this is not really an exact formula, and if you really want to, you can do some more advanced calculations and figure out better estimates for it. So finally, we can also think of, so we looked at a constant volume process, constant pressure process. And another type of process that we can look at is if an adiabatic process. So remember in the last chapter we looked at certain types of processes where the particular elements in this table were zero, right? We were looking at cases when constant volume meant this was zero. And now adiabatic means that actually heat is going to be zero. And the way that you actually, the way that this actually looks on a PV diagram is typically a line that looks like this. It's a little bit steeper than your isotherm. So it sort of comes down a little bit more sharply. And, well, by definition, the adiabatic Q is zero, so delta E is equal to the negative of the work. And I'm not really going to give you a derivation of this because it's kind of complicated and I think it will just confuse people. But there is an equation that tells you the relationship of basically, how the pressure and the volume are related along an adiabatic process. And the way that you derive it is basically you can split it into two parts. Say you got this adiabatic process, you can go along the isotherm and then down a constant volume, and then if you do a little bit of calculus, then you can get a relationship like this. So for an adiabatic process, then PV is equal to is a constant. So much like for an isothermic process, PV equals nRT. So if it's isothermic, then this is a constant, right? So for any isothermic process, so if you choose any 2 points, then along the isotherm, then this nRT will be a constant. So it will be along this line, whereas and so PV is a constant along this line, and hence in a PV diagram, P is equal to nRT over V. So much in the same way, in this case, for an adiabatic process, actually PV equals gamma P over is equal to constant. And so along an adiabatic process, which is a bit steeper, it basically follows this kind of condition. So it's P, the equation of the line will be P is equal to the constant divided by V over Cp over Cv. And then you can use the ideal gas law to rewrite this in terms of the temperature, if you like. So you just substitute PV into this relation, and then you can, substitute the P equals nRT over V into this relation, and then you can write it like that. This will be, again, given to you as a formula in the formula sheet. Okay. Right, okay, so I think this will be the last slide. And so just an example of this is a typical example. I think I already mentioned this example, is that if you open a champagne bottle, then a gas expands very quickly, and so there's not enough time for the heat to enter the gas. And so what you tend to see is this sort of kind of mist-like thing come out from the champagne. This is because of the adiabatic expansion of the gas. Because it's expanding it's doing work against the atmosphere. So because it's doing work is positive, but then the change in the internal energy will be negative of the work because it does work. It goes down, and remember, internal energy is related to temperature, so this is why the temperature will actually go down when you do this. So the gas will be kind of slightly cooler when you do this adiabatic expansion. Yeah?
What is, so the delta E
Yes.
for this table, for any bad process.
Right.
It's still negative W.
Yes. Yeah. So I didn't. Yeah. So maybe we can continue with the table next time. But basically, the way that you could work this out is that because this is work is PV, so in principle you could work this out as so this is pressure is constant divided by Cp over Cv, and then so this will be equal to that. So you would have to do this integral. Might be a little bit complicated, but no, it's actually not complicated. You just do that integral, and then that's equal to the work. And then delta E is equal to the minus of W here. Okay, all right. So we better finish up there. And so I'll see you next week for the quiz.